In this brief presentation, we're going to talk about the basics of particulate scrubbing, which is the removal of dust particles from air using water. Many people assume that scrubbing is a complicated process that only engineers can understand, but the basics of how scrubbers work is really quite simple. Scrubbing of our atmosphere occurs naturally when it rains. As rain droplets fall, they come into contact with dust particles and other gaseous pollutants that are in the atmosphere. The dust particles contact a water droplet, they adhere to it, and they fall to the ground with the rain droplet. This is nature's way of scrubbing our air. The term scrubbing is used here to describe removing particles from air using water. The term air is used in this presentation to describe any gas that we want to scrub particulate from. In many industrial applications, the gas is something than air, but for the purposes of this presentation, we're just going to call everything air. Flow is used here to describe the movement of some substance. It is usually contained within pipes or ducts. Flow is usually described as some volume per unit of time, like gallons per minute or cubic feet per minute. The term water in this presentation is used to describe the scrubbing liquor or liquid. In many industrial applications, something besides water may be used, but for this purpose, we're going to just use the word water to describe whatever our scrubbing liquid is. There are only two real steps in particulate scrubbing. The first step is to get the particulate to contact and become attached to water droplets. The second step is to remove the dirty water droplets from the airflow. A typical scrubber system is usually comprised of the following components: piping or ductwork that captures the particle-laden air from some process, the scrubber that is comprised of a contactor section and a liquid droplet separator, piping or ductwork that connects the outlet of the scrubber to the exhauster. The exhauster can be any fan or other air-moving device, and then finally a stack at the end of the system, which is the exhaust pipe for the industrial pollution control system. Now for a little more detailed look at the scrubber itself. Particle-laden air enters the scrubber inlet. Water is injected into the inlet or contactor section. In the contactor, we use some amount of energy to mix the water and air together. The more energy we use in mixing the air and water in the contactor, the higher the probability that dust particles will touch and become attached to water droplets. In other words, the more power we consume in mixing the particle-laden air and water, the higher the collection efficiency. Although it is something of a misnomer, the contactor is often called the Venturi, and the entire device is often called a Venturi scrubber. This is often a misnomer because many designs do not actually use a Venturi. A Venturi is a specific device or shape named after an Italian physicist, Giovanni Venturi, and is used as the contactor in some scrubber designs. Many devices described as low-energy Venturi scrubbers are really just cyclones with wetted walls and do not utilize a true Venturi. Many medium and high-energy Venturi scrubbers use flow constrictions like slots and orifices instead of using a true Venturi. Whatever the style of contactor used, we must use greater amounts of energy in mixing the air and water together as the dust particles get smaller and/or as the desired level of particulate removal increases. The rest of the scrubber is a droplet separator. This may also be called an entrainment separator. In this picture, we show a particular style called a cyclonic separator, which is a type of inertial separator or cyclone specifically designed for removing water droplets from air. The water containing the collected dust particles, called slurry, drains out the bottom of the droplet separator. The clean air goes out the top of the droplet separator. This is a 10-inch diameter Micek style entrainment separator or cyclonic separator. It's named after Gerhard Micek, who designed this device and patented certain aspects of it in 1976. The diameter of the vessel or the separator itself is 10 inches in this particular case. The way the separator itself works is this is essentially a type of cyclone or cyclonic separator. So the water droplets mixed with air enter the inlet here. It's made to spin by virtue of the inlet arrangement. So it has an involute inlet. The gas and water droplets spin as they enter the device by virtue of the air coming in the inlet. They spin around and they accumulate along the wall of the device, and as they're spinning, by gravity they fall into the drain. This device has two drains. It has a side drain here, you can see, and a center drain in the bottom. In this device, it's so short that the side drain does most of the work when it's running, and the center drain that's really used for draining the device when it's shut off to make sure there isn't water standing in it. And like I said, the clean gas is thrown to the wall and exits the top of the device, and this is the gas outlet here. This device does have an internal feature that helps make it work in this very compact space. It's got a spiral ring, a reverse spiral ring that's located right above the inlet, and this helps trap water droplets that are creeping up the wall of the device. Droplet free is the intent as it exits the device. This is our 10-inch diameter scrubber that we looked at a few moments ago. This is the gas inlet, as we already described. Air is going to be pulled in here, pulled through the cyclonic separator. It'll be pulled out this duct up here at the top and then over to the fan where it'll be blown to atmosphere. These are the two drain lines coming off the scrubber. This is the side drain, which is the main drain when it's running, and this is the center drain right here. And you'll be able to see liquid being collected, dirty liquid being collected and draining out of these hoses here. And we're going to run a couple experiments. First, we're going to run it without any water, so it'll be working just like a cyclone. It'll collect some of the dust. Then we'll run an experiment where we run it with water, and you'll see how much better it operates as a scrubber as opposed to a dry cyclone. All right, now we're going to turn it on and we're going to go ahead and run our first experiment, which is going to be completely dry. We're going to be running this just like a cyclone, separating particulate out of the air with no water. So turning on the fan, taking our cup of flour, baker's flour, and I'm going to dump it in the inlet basically all at once. It'll be over a course of 3 or 4 seconds. And you see the fairly significant plume that came up. Like I said earlier, the only thing that makes this a scrubber versus just a simple cyclone or cyclonic separator is we add water. So you can see in this, what we've done is we've added a garden hose and a garden spray nozzle to our test assembly, and elegantly, or not so elegantly, attached it with duct tape to this bracket just to keep it in place while we're running our test. All right, now I'm going to run the same experiment. We've got a cup of flour. I'm going to turn it on and we're going to run it again, dump it into the inlet of the scrubber as fast as I can. The only difference being is that now we have the water running, as you can see. So I'm going to turn the fan on. I'm position the spray nozzle and dump the dust. That's it.